Hi, this is Jamie, Assistant Line Cook here at the Rational Acoustics. Right now we're looking at an RTA in the background. I've got my USB pre-left being driven by the microphone back here. Now let's talk about the beast that drives it, just very shortly. We have much longer pieces of literature that will describe the FFT, and there are lots of places where you can go to learn about the FFT. But what is the FFT? Fast Fourier transform is a mathematical device for taking a time domain signal, a wave coming in, and turning it into a frequency domain, so the frequency domain data, so we can look at the frequency content of the signal. So that's what you're looking at here is my voice, the wave of my voice being transformed into the frequency content of it. Now there's a couple things about the FFT that you should probably know about. Probably the most important thing is that the frequency resolution of our data, and what I'm going to do is I'm going to pull up the raw FFT right here. So here's the raw FFT data coming in. The frequency resolution of the data is inversely proportional to the size, the chunk of time that we're taking. So the larger chunk of time, the larger the FFT that we use, the finer the frequency resolution of our data. And I can show you that really quickly by going into measurement configuration, and you can see, I'm just setting this up so you can see it. I'm going to change my FFT size. Right now I'm using a 16K FFT, a 16,000 point FFT. If I drop down the size of the FFT to a 1K FFT, all of a sudden I've got a much shorter chunk of time. I've got a faster FFT, it's going to run faster, but my frequency resolution drops down dramatically. You can see that especially in the low end. If instead, if I take my FFT size and bring it up to the largest FFT we run in real time, a 32K, which is about 2/3 of a second, we notice that our frequency resolution goes way up, but then the speed of the FFT, just because we're taking 2/3 of a second in each individual chunk, the reactiveness, the responsiveness of our measurement kind of drops. And so what we find is our default is running a 16K FFT. A 16K FFT, about 1/3 of a second per measurement, tends to have the frequency resolution we want and the responsiveness. Now here's the other thing about an FFT is an FFT is a linear beast, meaning that it's got each of its measurement points are linearly spaced, but we're logarithmic beasts in terms of listening. To us, a change from 40 cycles to 80 cycles, which is a doubling, that's an octave, sounds like the same amount of change as from 4K to 8K, but in linear terms, 40 cycles to 80 cycles is 40 cycles, whereas 4K to 8K is 4,000 cycles. I can easily show this to you by looking at our second signal here, which is, this is pink noise. Now pink noise, this is the console output showing up on just the raw log FFT data. It's sloping downwards because we get more and more data points up top, but pink noise is equal energy per octave. If I take this and instead of looking at it as the raw log data, I look at it on, say, octave banded data, we notice that I get a flat spectrum because pink noise sounds flat to us. It's equal energy per octave. And in fact, a quick way of looking at this, we could show you a bars view, we could show you a line view of the spectrum, or we could show you both, which is going to show you the raw FFT data and then the banded data. And it's pretty interesting to look at it in terms of the microphone data coming in. You can really see where this banding really affects the curve, especially up high where we have much more data points. If you look at just the raw FFT data, it de-emphasizes the high, whereas down low, the low is much more pronounced. And so, in general, the RTA is our measurement that really best corresponds with our hearing mechanism. So we want our data banded the way our hearing mechanism works. So in general, you want to work with a scale that is something that's fractional octave, either octave, third, sixth, 12th, 24th, 48th. I tend to run with the highest fractional octave, which is 48th octave. I'm going to go ahead and I'll back out, just go to regular bars, hit apply. So there's no averaging and 48th octave banding.